Welcome to this NCTS Algebraic Geometry Seminar. So today we are very happy to have Zhijiang from from Fudan University, and he is going to talk to us about surfaces of general type with PG equals to Q equals to 1.
Okay, thank you for the introduction. So I guess maybe 2 years ago, I was here also give a talk, but less about the surface of general type with PG equal to Q equal to 2. And then since that, so Professor Lin Xueyong from here discussed with me about the structural surface with PG equal to Q equal to 1. So today I'm very happy to talk about this here. And I think Xueyong is not in Taiwan for a while. I guess you haven't heard about this before. Yeah, okay. So I'm happy to give this talk here. Okay, so I hope. Okay, so everything is our compressed number field, C. So I will fix, first I will fix some notations. So S will be a surface, a minimal surface of general type. So then since S is minimal surface of general type, the canonical bundle Ks is bigger than F. And so the volume of S, the canonical volume of S is nothing but the self-intersection of K square. This is a positive integer. Okay, so for surfaces, there are some important directional invariants. So for example, we have the geometric genius. So this is the global section of the canonical bundle. And we have the irregularity. Okay, so by Hodge symmetry, this is also the number of global one form of OS. And since we will assume Q equal to 1, so we will always have R isomorphism. So we have the, so this is the R isomorphism. I think I guess everyone knows this notation. So this AS is abelian variety of dimension QS. So this is the universal morphism to abelian variety. Okay, so there is another very important bilateral invariance. That's the holomorphic Euler characteristic. So we can the holomorphic Euler characteristic. So again, by cell duality, this is also the Euler characteristic of the canonical bundle, and we can write it down by root formula plus C2S. Okay, so here what is for surface of general type? This is special because so we know K square, the volume is a positive integer. So by Miyake-Yauzi inequality, we know also C2 is a positive integer. So in any case, this is a positive integer. So this again is positive. Okay, so this is also important. Okay. Okay, so basically these are the invariants I will need for today's talk. So then there is this question, very old question. So in what sense can we classify surface with given bilateral invariance? Okay, can we classify surfaces with given bilateral invariance? Okay, so of course one need to make sense of this kind of question. So for example, let's look at the picture for dimension 1 case. Okay, so should I do? Oh, okay. So okay, maybe I should put it down. Okay, so maybe let's look at the case in dimension 1. So in dimension one, so we don't need this kind of bilateral invariance. Okay, so basically we have only one invariance. That's the genius of the curve. Okay, so we have G is the genius of curve. So now C is a curve, smooth curve. And we also have the global section canonical bundle is also equal to G, and G is the irregularity of the curve, and the canonical volume, the degree of the canonical bundle is 2G minus 2. So everything is determined by G. And so there's no relation, no other invariance. And then moreover, so we also know that there exists a cos-modular space Mg parametrizing curves of genus G. Cos-modular space means that it has certain modular property, but I'm just going to say the isomorphic class forms a modular space, and we know that this Mg is actually irreducible variety, okay, which is an irreducible variety. Okay, so this is actually a very deep result. It says that all curves of genus G can deform to each other as smooth curves. And this is a very deep result. So over C, I think this result was first proven by analysts. They used Teichmüller's theory to prove this result. And for algebra theory, it's only until 1989, Deligne and Mumford, in their famous paper, they gave a proof in all characteristics. They actually introduced the stable curve, and then they are able to prove this result in any field, algebraic closed field. Okay, so this is actually a very deep result. So a priori, from the projective geometry of curves, it's very difficult to see that all curves of genus G can deform to each other. Okay, so this is the kind of result we want to prove, we want to show in higher dimension, but it turns out that in higher dimension, this is an extremely difficult question. So okay, so maybe for the good thing is the following. The first good news is there is a result of G-cycle. She says that there exists a fixed positive integer n. There exists a quasi-projective scheme. So parametrizing, this is also a cos-modular space, but I'm just saying that this parametrizing surfaces. Okay, so maybe I should put canonical surfaces of general type whose volume is n. Is okay. So the point is that first of all, this is a scheme of finite type. So that means that if we fix the canonical volume of the surface, then there are at most finitely many deformation type of surfaces. And then what is important that this is a quasi-projective scheme, but it's no longer a variety because the deformation of surface is very complicated. It no longer it could be a scheme. And okay, so this is the good news, but the problem is that the scheme structure is very complicated. First of all, the scheme structure is complicated, very complicated. Second of all, even we forget about the scheme structure of this scheme, and we only consider the variety structure. So it's impossible to determine how many components, connected components or irreducible components of this scheme. It's even difficult to determine irreducible or connected components. Or Mn. Okay, these are two remarks. So of course we can put this skin is we only consider the volume, but we can also put other biological invariants. So it's clearly. So since this PG and QS, they are deformation invariants for deformation of canonical surface. So we know it's clear that this MN we can always write down as the disjoint union of. So maybe I could I write it in this way. So I put this number. This means the canonical volume Ks square. I can write it as the disjoint union of Ks square and PG and Q. So we have three numbers. One is the volume, and then we have the geometry genius, and then we have the irregularity. Okay. So since the geometry genius and the irregularity are deformation invariants, so these are disjoint union. Okay. So but still, if we fix the geometry genius and the irregularity, it's still very difficult to determine how many components it has. Okay. So we will see some examples. Okay, so before I'm going to talk about examples, I should say that so for curves, everything is determined by the genius. For surfaces, we have several biological invariants, but there are relations among them. So they are not totally independent. Okay, so these relations, the study of these relations are called geography of surfaces. So maybe I should say something about the geography. So so there are relations. Actually, mainly relations between biological invariants. Some of them old, some of them are new. So, for example, we have the Lotto inequality. So this Lotto inequality says that the volume of surface is at least 2 PG minus 4. Okay, so it makes sense. So if the genius goes high, and we can estimate the volume. So this is the Lotto inequality, and this is proved by Max Noether. And then we have some similar Lotto inequality, which are different, but also in this direction. So, for example, I can mention that there is also the de Baha inequality. So de Baha inequality says that if the irregularity of the surface is non-zero, then we can improve this. It's positive, then K square is at least 2 PG. Okay, and so another important inequality in this direction is if the irregularity is still bigger, then we can still improve this inequality. So this is called the Savalli inequality. So the Savalli inequality says that if the ASR panismorphism is genetically finite onto its image, so then the volume is at least 4 times the holomorphic Euler characteristic. So I can also write it as PG minus Q plus 1. Okay. So these are all inequalities which give the lower bound of the canonical volume. So they are similar to each other. The nature is actually the same. Okay. So I should say all these inequalities are sharp. All these are sharp. Okay. So for example, and also when the equality holds, the structure of surface are actually simple. So this is a very general phenomenon. So in general, if we have some interesting inequality, and when equality holds, it's usually interesting and a little bit easier to determine the structure of the variety. Okay. For example, Horikawa in the 1970s, she determined all the surfaces in this when the equality holds, and these surfaces are nowadays called Horikawa surfaces. Okay. On the Newton line. Okay, and also, I mean, the Baha inequality, when equality holds their work, how to characterize those surfaces. But it's irrelevant to this talk, so I will skip that. But another important thing is when several equality holds, so one actually can classify the surfaces. This is the work of Baha, Pardini, Stopino, and also independently by Liu Xing and Zhou Kang. So it's around, I think, this is much later, around 2016. This says that if several equality holds, for S, then we have this R-branching morphism. So then this surface is actually, the R-branching morphism is actually a double cover. Then actually, so we have the R-branching morphism from S to AS, and clearly we have the contraction from S to the canonical singularity. So S, this is means the canonical model of S. Okay, so we know that for canonical singularity, the fibers are just minus two curves. They are rational curves. So this morphism certainly contract all the rational curves. So it factors through this map. So we can factor through this map. And what this says that in this case, the canonical model to AS is actually a flat double cover. And maybe I should put a bar. Then okay, so how to okay, so A bar is actually a flat double cover. Okay. Yeah. So actually this gives how to say a colorization for surface on the Savory line. When you have a canonical surface which is a flat double cover abelian surface, then automatically the Savory equality holds. The volume is actually equal to the 4 times the chi. Okay, so this is the characterization. Actually, I should say the Savory equality holds for S if and only if A bar is a flat double cover. Okay. Okay, so I will use this characterization, so I explain the structure now. But there is another important inequality. This is a completely different direction. So let's call it the Miyaoka-Yau equality. Okay, so this is the different direction. It says that in general, for any surfaces, the 9 times the holomorphic Euler characteristic is bigger than k square. So if we put a rotor inequality here, we can also write as 3 times C2S is bigger than k square. Okay, so this is Miyaoka-Yau's inequality. And again, this is a sharp inequality. And Professor Yau proved that when equality holds, this surface should be a Borel quotient. Implies S is a Borel quotient. Okay, so this set of inequalities, they actually give strong descriptions about the moduli space of surfaces. So we see that once we put k square, pg, and q they are no longer independent. There are some relations between them, among them. Okay. So as I said, in general, it's very difficult to determine even the kinetic components of this moduli space. So now let me give some example or maybe also we can see that as an open question. So from the case of curves, one thinks that when the genus is small, it's easier to describe the curve. Okay, for example, genus 2 curve is nothing but a double cover over P1 branched over 6 points. And from this point of view, we can easily describe the moduli space. Okay, and when G becomes higher, then it's more difficult to describe the curve. I mean, for G is sufficiently large, this MG is not even unirational. So basically, we cannot write down uniform way of equations for the curves. Okay, so then when we expect similar things holds in higher dimension. So in higher dimension, we may expect that when the bidirectional invariance is small, then it's easier to describe the curve, the surface. But I will show that this is in fact not true. For the surface with the smallest bidirectional invariance, it's actually very difficult to determine the structure. But on the other hand, for surfaces, when the equality holds, it's relatively easier. So that's a very interesting phenomenon. Okay, so let me show what the question. I mean, okay, so maybe I should say example or question. And question. So now we assume, as I said, the holomorphic Euler characteristic is a positive integer. So we may ask, what happens when the holomorphic Euler characteristic is the smallest possible one? Okay, so okay, so then we can write as okay. So first of all, Milka-Yau implies that these surfaces are bounded. So it says that the canonical volume of S is smaller than 9. So this surface is actually bounded. There are only finite many, up to deformation, there are finite many surfaces satisfy this property. The volume is between 1 and 9. And then we can also write the holomorphic elastic as 1 minus QS plus PGS. Okay, so holomorphic Euler characteristic equal to 1 exactly means that PG equal to Q. Okay, so since these surfaces are bounded, so this number should not be too large. It's actually we have bound for this number, and a priori is not clear. But I think first, Bouvier shows that in this case this number is at most 4. So there is argument by Bouvier. Then under this assumption, PGS equal to QS is smaller or equal to 4. Okay, and this there is actually quite a beautiful argument to show this equality. So the reason is the following. So actually the argument goes as follows. So we can, the idea is the following. So we can consider the linear map. So if we have one form and we take the wedge product, we have 2 forms. So okay, so we can consider the linear map from okay, so we have this natural map. And okay, from this map we get nothing, but we can try to take the polarization. So we can consider the rational map. Okay, so okay, so here my notation is this polarization means the subspace. Okay, so maybe I should put a sub here. Usually I take the quotient, but here it's easier to understand it as a subspace. Okay, so we can consider this rational map, this no longer morphism, because certainly there are kernels. We can compute the dimension. Okay, so but for here we have another map. This is the Bleecker embedding. This is the Bleecker embedding. Okay, and so we can count the dimension. So the dimension here, this is the dimension is 2 times PG minus 2. And the dimension here is PG minus 1. Okay, so then we have an induced rational map. Okay, so for Grassmannian, we know the Grassmannian has pk number 1, and the projective space has pk number 1. So so basically it says that when the dimension of the Grassmannian is bigger than this space, this should be a rational map. It is no longer a morphism. Okay, since is 1. When the dimension is strictly larger than PG minus 1, this map is phi is just a map, is not a morphism. So if you have a higher dimension variety, there is a morphism to a lower dimension variety, then certainly the pk number should be at least 2. Okay, you have some number which is not ample from the base. Okay, so phi is not a morphism exactly means that there are 2 one form whose wedge product is a 0 2 form. Okay, so this is condition. This numerical condition exactly means that when PG is bigger than 4, bigger at least 4, then this is no longer a morphism. Then this is equivalent to say that there exists independent one form omega 1, omega 2, such that omega 1 wedge omega 2 is 0. Okay, so this argument says that when the variety has the geometry genus at least 4, then we can find 2 independent one form whose wedge product is 0. And from this point, that is clear. We can apply the famous Castelnuovo-de Francis lemma. Okay. Then Castelnuovo-de Francis implies that this one form, they actually comes from a base curve. They exist the fabulation such that omega 1, omega 2 belongs to the base. Okay, so then it's very easy corollary. So this curve certainly has genus higher at least 2. Okay, so it's very easy. Then it's easy to see that. This fabulation is a trivial fabulation. Okay, since this F S to C is a trivial fabulation. Okay, because the reason is that there is a general equality says that the holomorphic characteristic of the S is so okay, maybe I should say this way. So if we put F a general genus fiber here, then the chi OS is bigger than chi OF times chi OC, and then plus some contribution of singular fibers. And the contribution of singular fibers is always positive. Okay, so the chi OF is at least 1, the chi OC is at least 1. So this is 1 at least bigger than 1 plus something positive. It means that there is no singular fibers, and the base and the fibers are all genus 2 curves. Okay, so from this we can see that actually when the PG is at least 4, then the surface is actually isomorphic to a product of 2 genus 2 curve. Actually, then it means that it shows that S is isomorphic to a product of 2 curve. Okay, both are genus 2. Okay, so basically this is what Bouvier shows that when PG equal to Q, then it's at most 4. Okay, so this is nice. It says that at least we see when PG equal to Q equal to 4, this the modular space is actually irreducible. Okay, they actually they're determined by two genus 2 curves. Okay, so after that, people try to continue what Bouvier did for when people try to see what happens when the PG equal to Q smaller than 4, 3, 2, 1, or 0. So okay, so when this number is 3, this is already solved. So this this is solved. This is the work of Heiken, Pardini, and also Pirola. I think their work is around 2001 or 2002. So when this number is 4, then this is a irreducible family. The modular space is easy. You can also see that the volume is 8. Okay, is 8. And when PG equal to Q equal to 3, there are actually 2 families. So there is one family which is so S2C, where C is a genus 3 curve. So another way to see this surface, you can consider principally polarized abelian threefold. So in this abelian threefold, the theta divisor is actually bidirectional to the symmetrical product of genus 3 curve. Okay, so then it's very easy to verify the PG equal to Q equal to 3, and the volume is the PG equal to Q equal to 3, and the volume is actually 6 in this case. Okay, there is another family which is slightly difficult to describe, but it's also easy. But also, maybe I should put this way. So this is again a product quotient. So we can write it as C1 times C2 quotient by tau 1 times tau 2. Okay, so here well C1 is genus 2, C2 is genus 3. And this tau 1 is an involution on C1, and C1 there is a ramified double cover over an elliptic curve. This tau 1 switches the fibers. Okay, and C2 there is a eta cover. Eta double cover over a genus 2 curve. And again, this tau 2 switches the fibers. Then the surface is just the C1 times C2 quotient, the diagonal evolution. And then it's easy to verify the PG equal to Q equal to 3. But in this case, since this is eta to a product of 2 curves, one can see that the volume is 8. In this case, the volume is 8. So we have more surfaces when the environment is smaller. Okay, but they show that these are the only surfaces which satisfy PG equal to Q equal to 3. Okay, so when seeing that when the environment goes down, we have more. It's possible to construct more surfaces with this property, and we can see PG equal to Q smaller than 2. So the 3 cases are completely open. Okay, so maybe I can draw maybe I can write it in this way. You can see to what extent they are still open. I write PG here, and write the volume here. This is 2, this is 1, and this is 0. Okay, so in any case, the volume is at most 9. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so when we consider when the geometry genus is 2, so the summary tells us that actually the volume is bigger than 4 times the chi. Okay, so it is irrelevant. There is no case for PG volume equal to 1, 2, 3. There is no such surface. This is because it's the Savory inequality. And the Bhatt inequality says that when PG equal to Q at most of 1, there is no surface with volume equal to 1. So this is irrelevant. Okay. By the geography, you already know these are empty. And Savory inequality, the characterization for Savory inequality tells us that these surfaces are clear. They are double covers or abelian surfaces. Okay. So this is okay. This is already known. And so 5, 6 cases, they are known. They are actually only solved by myself and my collaborators 2 years ago. So this is okay, okay. So this is the work of myself and my collaborators. And then these are open. Okay, so we have still 3 cases which are open. Okay, so I will mainly explain this part. I should say these are okay. They are basically work of Catanese and Professor Catanese and his collaborators. So there's no space to write down all the names because it's a long list. So I will maybe talk about it later. But then we see that they are all, after that is, okay, maybe this one is okay. Okay, okay, so you see we have many more open cases. Okay. And then for PG equal Q equal 0, basically everything is open. So okay, so only this one is open. Is solved. So I should say the reason this tool is okay is not the effort of algebraic geometers. They actually the deep result of Yao, which Yao says that when K square is all equal to 9 chi is a Ball quotient. Okay, so then basically the fundamental group of this surface determines the structure of the surface. And then these are, I mean, these are solved because of the efforts of some number theorists like Plaza and Plaza Yang, and yeah, so these are okay. But so you see that for this seems really mad question, surface with holomorphic Euler characteristic equal to 1, there are so many cases which we don't know. They are still open. Okay, so maybe I can, when I'm going to explain basically the structure of surface here. This is today's topic, okay? This is today's topic. But before that, let me just explain a little bit what happened for PG equal to Q equal to 2. Okay, so in this case, so I put a remark here. When PG equal to Q equal to 2, we still have the Arban's morphism. So when we consider the Arban's morphism, we may assume they are surjective. Okay, may assume is surjective. Okay, the reason that we can assume this is surjective is because this is abelian surface since Q equal to 2. So if this is not surjective, then the image is only a genius 2 curve. Okay, and then a very similar technique as I said here. Here you can see that the structure of the surface is basically determined. Okay, they are kind of product quotient, even product eta quotient. So the structure is simple. So we may assume the surface is in the urbanism is surjective. Then in this case, so the modular space can also be split into different components, which is the degree of the urbanism. So actually, the degree of this urbanism is a deformation or even topological invariance of the surface. So one can see this by consider the wedge product of the of one form. Okay, so actually this degree of S is a topological invariant. OS. So when basically the topology determines the degree of the urbanism. So this is because we can consider wedge 4 H1 SZ to H4 SZ. We can consider this map, and you can see that the image is this is isomorphic to Z. So the image is actually a subgroup, and the generator is just the degree of the urbanism. Okay, so it's easy to see that. This argument is due to Professor Catanese. So we can further define the direction invariance. And then is basically to determine the structure of the surface, we need to study the degree of the urbanism. Okay, so in this case, the degree is, for example, when volume is 4, the degree of AS is 2. And the degree, when the volume is 5, the degree of AS is 3, and they are irreducible modular space. And when volume is 6, the degree could be 2, 3, 4. This is what we proved. Okay, and for each degree, there are still some different components. So it's actually very complicated. So for remember, I can say that M422 is actually equal to M4222 irreducible. M522 is M3522. So okay, so I need to say that this kind of surface was first constructed by Professor Longkai Chen and Heiken, so many years ago. And then now we prove they are the only surface with volume equal to 5 and PG equal to Q equal to 2. Okay, and but M622 is actually already much more complicated. So it's 6222 3 4. It means that the urbanism could have been degree 2, degree 3, degree 4. And even for degree 2 case, there are already several connected components. It's not irreducible. Okay, this is not irreducible. Okay, so anyway, this remark just says that I mean, the structure of surface is nearly complicated. We don't know how many direction invariant, how many deformation invariants we need to put to make sure that the corresponding modular space is irreducible. There are so many different invariants. Okay. Okay, so in the remaining time, I will explain this line. We don't know much. So Professor Catanese and his collaborators solved the 2 and 3 case. And with Xueyou, we made some progress here, but we haven't completely determined all the surface here. Okay, so let me explain what we have done. Okay, so from now the PG of the homogeneous of the surface will be 1, and we know the volume is between 2 and 9. Okay, so in two cases we consider the isomorphism, which is we may assume they are genetic finite or surjective. Okay, but now the homogeneous is 1, so we have the isomorphism is actually a fibrilation onto an elliptic curve. So we have this isomorphism. Okay, so it's a the isomorphism is now is a dimension 1 abelian variety, so it's an elliptic curve, and it should be a fibrilation. So otherwise, by Stein factorization, we know it maps to a curve of genus higher, which is impossible. Okay, so now I will fix F, the genus, a general genus, a general fiber. OS. So okay, so I mean you can see that if we consider small deformation of the surface, so we can construct the relative isomorphism of the surface. So the genus of F is again a deformation invariant. Okay, the genus of F is a deformation invariant. OS. So it's in order to bound the deformation class OS, it's important to bound the GF. We need to understand what kind of fiber it could be. Okay. Okay. So let me see. So there are this result. I mean, the first theory is due to Catalese, and I think also Horikawa. So basically, this says that when Ks, the volume is 2, Pg equal to Q equal to 1, this GF can only be 1. Can only be 2. Okay. And so we have this morphism, and this is 2, so the push forward of the canonical bundle is a rank 2 vector bundle. Is a rank 2 degree 1 vector bundle. S canonical, there is a morphism. Is a flat double cover. So this theory determines the structure for surface of volume 2 and Pg equal to Q equal to 1. Okay, so so of course in that time they proved by different methods, but today we have some we can use some important new tool to give a very simple proof why the genus is at most is 2. So the genus should be at least 2 because the fiber is a curve or is a general type curve, so it should be at genus at least 2. Okay. So what we can use is, for example, we can use this result of Shaw. This is Gang-Shaw's slope inequality. So in general, it says that given a fibrilation from S to a curve, then the relative canonical bundle, I mean minimal. Then the relative canonical bundle is actually a left divisor. So it says that the self-intersection of this line bundle is at least 4 times minus 4 GF times the degree of. Okay, we have this inequality. So in our situation, we just consider the Arbanese fibrilation. Then the relative canonical bundle is just the canonical bundle. So then in this situation, it says that the volume in this case is 2, is at least 4 minus 4 GF. This is just 1. The degree 1 is easy because the chi is 1, okay, times 1. And we see immediately the genius of the fiber is at most 2, which implies GF is 2. Okay. Okay, so once when they determine the genius of the fiber is 2, then the structure is easy. Okay, so I forget ample effect amount. Okay. Okay, so once we know the genius 2, then it says that so this is a vector bundle of rank 2. Okay, so now I need to introduce another result, which is a very classical result. This is called the Fujita decomposition. Okay, the Fujita. The Fujita decomposition says that it's a very general result. It says that if we have a smooth projective variety over a curve, then the push forward of the canonical bundle, relative canonical bundle, sorry. So this is a left vector bundle, okay? But it's not only a left vector bundle, but we have a canonical decomposition, which can be read as U direct sum of A, where A is an ample vector bundle, and U is a unitary vector bundle. Unitary vector bundle means that this vector bundle is constructed via the representation, a unitary representation of the fundamental group of C. Okay, U is a unitary vector bundle. So this is the quite general Fujita decomposition. But if we apply in our situation, so our situation is just a surface to an elliptic curve. Okay, so then Fujita decomposition says that S star omega S is U direct sum of A. But since the base curve is an elliptic curve, so we know the elliptic curve, the fundamental group is just is abelian group. Okay, so all the irreducible representation is dimension 1. So this unitary part can be read as a direct sum of torsion line bundle. Where Pi is a direct sum of torsion line bundle. It is a torsion line bundle, sorry. Okay, so so in this result for the volume equal to 2 case, actually the unitary part is 0. We only have the ample part. I will explain this the reason later because it will appear in our case when the volume is 4. But then when we see this result, then there is no unitary part. We only have the ample part. The ample part has degree 1 is easy because. So in this case, when k square equal to 2, the unitary part is 0. And we have only the ample part, then the degree of the ample part is just the chi of S star omega S. This is also equal to by the Lorentz spectral sequence plus chi R1 S star omega S. And we know by relative duality, this is just the OE. So we see the degree is equal to chi omega S equal to 1. Okay, so then we see this vector bundle is actually a stable vector bundle of degree 1. Yeah, and after that, it's easier to see this is the canonical model to the polarization. We have the relative canonical map, which the relative canonical map gives the flat double cover structure. Okay, so this is the story for volume 2 case. And so from the this proof, we see that it's important to understand the structure of the canonical bundle. If this is the key point here. Why is the fibrilation? So this is okay. So we have this non-trivial morphisms, and if this is a lot of fibrilation, we can consider the Stan factorization. So either this genius of C is bigger than 2, then the irregularity of S is bigger than this QC. Is bigger than 2, it's impossible. If the genius of C is 1, then it's again abelian variety. It's a contradiction to the universal property of Arbanis. Yeah.
That's not proper. There's 100 dimorphism.
This is actually, I mean, these are anyway, this is a holomorphic map, okay? And these are projective varieties. And the holomorphic objects are actually algebraic. Sorry? Yes, the image cannot be a point because it is a general fact that the Arbanese image generates the abelian variety. Yeah, it cannot be a point. Okay, so I'm now going to talk about pk square equal to 3. But as a fact, I should say that in this case, so this is several work, several people's work. This is due to Catalese, Chiliberto, several papers, and finally there is a work of Catalese and Pignatelli. Okay, so there are several papers from 1990s to 2002, I guess, I think. So basically what they show is GF is could be 2 or 3. And 3, 1, 1, the modular space can be written as a disjoint union of 2, 3, 1, 1, 3, 3, 1, 1. And this one is irreducible. This part is actually the easy part when the genius is 3. This is the work of Catalese and Chiliberto. And this modular space, they have several irreducible components. Several. I don't remember the exact numbers, but it's not a big number, maybe 3 or 4. Several irreducible components. So actually, at the beginning, Catalese Chiliberto conjectured that this also form an irreducible family. But then Catalese Pignatelli, they realized that there are actually several components. Okay, so, again, the key point is first to determine the genius of the fiber. Once the genius of fiber is determined, then is one can proceed to construct the surface and try to describe them. Okay, so so now I can present our main result. Okay, so the first result is the following. So let S be a minimal surface of general type with KS square equal to 4, PG equal to Q equal to 1. Then the genius of the Arbanese fiber is at most 5. And we also show that when the genius reaches the top possibility, is irreducible. And it's actually genetically smooth of dimension 3. Okay, we can completely describe this kind of surface. Okay, so the proof is following. I follow the similar strategy. So as I said, so we have the Arbanese fabulation, which is a morphism, which is a fabulation, and then we have this vector bundle, which can be decomposed as the unitary part and the ample part. And clearly, the rank of this vector bundle is just the genius of the general fiber. Okay. And we need to analyze this vector bundle. Okay, and of course, by the general argument, we know the degree of the ample part is just 1. Anyway, this ample part is a stable vector bundle. Okay, so this is the our starting point. Okay, so but I explained before for genius when the volume is 2 or 3, this unitary part doesn't exist. But when it's 4, it exists. Okay, so let's reach our second result. So okay, so maybe I should give a name. So I will define. We say a surface S with Q equal to 1 has non-trivial Fujita decomposition. If the unitary part of the push forward canonical bundle is non-zero. Okay, so we expect for general surfaces, the push forward of the canonical bundle is ample, but there could be it could happen that this U is non-zero. When U is non-zero, we say it has non-trivial Fujita decomposition. This is the definition. So in order to prove theory A, so we first deal with the case where the Fujita decomposition is non-trivial. Okay. So this is actually okay. So assume Qs equal to 1, and S has non-trivial Fujita decomposition. Then the volume of the SOS is at least 4 times chi OS. We have this similar this inequality, which is very similar to the Savory inequality. Okay, and when inequality holds, okay, so I should say equality holds if and only if the canonical model S admits a flat double cover. A flat double cover from the canonical model S to a bi-elliptic surface, where V is a bi-elliptic surface. So let me explain this theory B is very useful, but the proof is actually simple. So I can explain. First, I will explain the proof of theory B. After that, we can assume the S has trivial Fujita decomposition, namely the canonical push forward the canonical bundle is stable. Then we can prove theory A. Okay. So let me first explain the proof of theory B. Okay, so before that, I should explain what is a bi-elliptic surface. So it has different names in the literature. Sometimes it's called a hyperelliptic surface. So these surfaces are actually, if we look at the any cases the classification of surfaces. This is one kind of the surface with Coulomb dimension 0. Okay, so by elliptic surfaces, or sometimes it's also called in. I'm thinking maybe in Japan it's called hyperelliptic surfaces. Okay. So both names exist anyway. Elliptic surfaces. Yeah. Okay. So this surface. So it. I mean, this V has a KV numerically trivial, numerically equivalent to 0, and QV equal to 1, equal to geometry genius equal to equal to 1. Okay. And the canonical bundle is non-trivial, so the PG equal to 0. So so this surface structure is very well understood. They are just quotient by a product of two elliptic curves. So V is isomorphic to B times F modular group, where G is a subgroup of B, and it acts on B by translation. Okay, and acts on by translation, and G acts on F faithfully, such that the quotient is P1. So this is the basic structure of V, and we can also then determine the group G. There are 7 types. So G could be actually we can write down the type, the deformation type, or the modular space type. 1, 2, 3, 4, 5, 6, 7. There are 7 types. In the type 1 case, the G is Z2. Then type 2 case is Z2 times Z2. Z4 times Z2. Z3 times Z3, and Z6. Okay, so I mean, this gives the actually we also have we can describe the modular space, the coarse modular space of these surfaces. So these surfaces are quite well understood. Okay, so basically, if we have a flat double cover, okay, so I should say a flat double cover branched over ample curve, but this is clear since S is canonical, is a general type. Okay, so I omit this word here. Okay, so okay, so now I can try to give the proof of theory B. Okay, so we have the non-trivial part, so we can write it as direct sum of Pi, and with some stable ample vector bundle of degree 1. So the first thing is, so we can try to kill this torsion line bundle. Okay, so we have this morphism. This is AS. So anyway, we on the base we can try to find eta cover which kills all the Pi. This is eta cover such that pi star Pi are trivial. We can choose this kind of eta cover, and we do the base change. We make a Cartesian diagram here. So immediately one sees that once we kill the irregularity, the PR here, then if we try to compute the irregularity of S prime, we see, so I write it as F. So first observation, since this is a Cartesian, is F is still Fabrician. Okay, and secondly, so the irregularity of S prime becomes larger. So it is equal to H1 or E prime plus H1 H1 pi star. So this is so maybe I should write I equal to 1 to R. So it becomes 1 plus R. Namely, if we have the unitary part has rank R, then if here all the torsion line bundle, the irregularity becomes 1 plus R. Okay, so it has a larger irregularity. So it means that this fibrillation F is no longer the Arbanese fibrillation or no longer the Arbanese morphism or S prime. So we can consider the Arbanese morphism here. Of course, we fix the Arbanese fibrillation. We have this diagram here. Okay, and write it as G. Okay, so we have this commutative diagram. So maybe I can write G as the Galois group of the pi. Also pi's. Also the Galois group of pi's. So we have automorphism, which is the abelian group X on S prime. But it's so since the Arbanese morphism is actually a canonical morphism, so each automorphism here, actually here we have a group of if we have you see that you will fix the automorphism sigma here. So automatically by the universal property of the Arbanese morphism, this morphism descends here. Okay, there is a sigma A here. So it means that this automorphism group Gx here is no longer, of course, this automorphism is induced by the action here, but it also descends on action here, okay, by the universal property of S prime G X on S prime 2. So it means that this Arbanese morphism is actually a G equivalent morphism. Okay. Okay, so basically now we are basically done because so our assumption is that so we want to compare the volume and the chi, but both invariants. So if we take eta cover, they just multiply by this degree of the eta cover. Okay, so we know that since okay, so I should also say that this S prime has the S prime is genetically finite onto its image. The reason is that if not, it maps to a curve. Okay, then this map is mapped to a curve, and this curve generated S prime. So this curve should have genius at least 2. Then the morphism to E is no longer a fibrillation, which is a contradiction here. Okay, so this S prime should be genetically finite. So otherwise, F is not a fibrillation. Okay, so now we can apply the Savory. The Savory inequality says that it implies that the Ks prime, the volume of Ks prime is bigger than 4 times chi OS prime. And this is just the G times the Ks prime, and this is just 4 times the chi OS. So we can divide the order of G, and we get this inequality here. Okay. So this inequality just follows from the Savory inequality. Okay, so then what we know when the Savory equality holds, the Arbanese morphism should be abelian surface. It means the rank R should be just 1. It's abelian surface, and we also know that we have this. We can descend the Gx also on the abelian surface, so we can descend. Okay, so then. Hence, so when equality holds, R equal to 1, and we have this double cover here, and then we can go back. And again, this is E prime to E. because the QS should be is 1. So we see that from this diagram, you see this quotient is a free quotient. And by QS equal 1, we know the Q of this one is again 1. So this quotient should be a bielliptic surface. Is a bielliptic surface. Okay, so let's basically the proof of theory B. Okay, so okay, so here. This is a simple result, but it's actually it turns out that it gives at least 7 different kinetic components of the modular space. Okay, so let me just put some remarks here. Okay, so now, so after the, let me just give some remark. Then, so when, so under this assumption, so we know the surface is determined by is a flat double cover. The canonical model surface is a flat double cover of this bielliptic surface. Okay, so the isomorphic class of S canonical or S is determined by the isomorphic class of the triple data, where V is by the isomorphic. Okay. Where V is a bielliptic surface. L is the ample model. And D is the branch locus. D belongs to 2L. It has so D is just the branch locus. So it has what are called there are also some names which are called has a simple singularity or negligible singularities. So even curve has negligible singularities. It precisely means that the double cover has a canonical singularity. It's the equivalent definition. Okay. So from this point of view, we can actually describe completely the modular space for these surfaces. Okay. So then I can say that this M4 1 1. So we have some further decomposition. This is non-trivial. Fn. Fn means the Fujita non-trivial and the disjoint union of Fujita trivial. And they are disjoint union because if it has Fujita decomposition is non-trivial, this is also a topological invariance. Okay. So basically, you can see this fact from the fundamental group of the surface. This is actually not a, I mean, this is not a closed condition. This is actually a closed open condition. So the modular space splits. And on this part, we have several, it has exactly 7 kinetic components. These 7 exactly correspond to the type of the bielliptic surface. But I should say this is a non-trivial, very non-trivial result. Because the reason is that for this bielliptic surface, so the Lehonsev group is actually trivial. So Lehonsev group, the definition is the Pika group modulo numerical equivalence. These are very easy to describe. They are just Z2. Okay, so they are just all isomorphic to free abelian group. They are generated by there are 2 fibrillation. One fibrillation is the Arbanese fibrillation. The other fibrillation is to the P1. Okay, but they actually have torsions. many of them have torsions. So it's not completely trivial that the modular space just corresponds to the isomorphic type of the biallelic surface. Okay, because we have torsion. For example, in this case, the torsion group is J2, direct sum J2. So there are torsions in other cases. So I mean, it's anyway. So we get in this case we get when the Fujita decomposition is non-trivial, we get 7 kinetic components corresponds to the biallelic surface. But what is interesting that these surfaces are not new. They have already been studied. They have been studied by other people. There are 4 of them studied by Pignatelli. And there are 3 of them studied by Lin Songbo, a former student of Catalese. So they have been constructed before, but with very different methods, completely different methods. Okay. And we show they just constructed these surfaces, but we show these surfaces they are exactly the surface with non-trivial Fujita decomposition. So that's the difference. Okay. So now I have still a little bit of time. Maybe I will explain. I will explain this part. This part maybe is it's I don't have enough time to say anything. Okay. So for now, I can assume the push forward the canonical bundle is actually a stable vector bundle, stable. With slope of rank equal to GF and degree equal to 1. Okay, so that's the basic assumption. So first of all, there is an argument of Kono says that in this case actually the okay. So let me show you the first step, step 1. So the step 1 is consider this. So we have the canonical map. Okay, so this is just the relative multiplication of the sections. Okay, so if we look at this bundle map, so we have some interesting facts. So let me just check. So if we compare the degree and the rank, so this vector bundle is ample. So this is there are many ways to see that because this is a canonical bundle plus something bigger than F. It has no higher cohomology, so it's clear this is ample. So the degree of this vector bundle is just P2F. Okay, so P2S is just chi OS plus K square. So it's 5. So degree is 5. And since we assume the genus is GF, so the rank is 3GF minus 3. So, and then we know that this vector bundle is easy to compute. This is 2GF minus 1 probably. And the degree is just GF minus 1. Okay, because this vector bundle is now the vector bundle is of slope of 1 over GF. So if we take the symmetrical power, then it's 2 minus GF, 2 over GF. So this gets the rank and the degree. So this is semi-stable. Because the symmetrical power of stable vector bundle is semi-stable. Okay, at least in calculus 0, this is clear. So it shows that the slope here is at least then 3GF minus 3 over 5. The slope should be at least this slope should be bigger than 2 over GF. Okay, so this is I should say this is genetically surjective. Okay, so this is genetically surjective. This reason is for curves, you know, the 2K is generated by the global section of 2K is generated by the section of K. Okay, so this is Lotus theory. So this is genetic surjective. So then we have this inequality. We see immediately that maybe I write down this is 5. 3G minus 3. Okay, so it gets that GF is at most 6. So this argument is not new. This is due to Kono. And this is actually a general. What you need is just this vector bundle is semi-stable. Okay, this is semi-stable in all cases because this is ample degree 1, so it's guaranteed. Okay, so this is not what we want. So actually, for a very long time, people don't know whether or not 6 can be reached. So then we ruled out the possibility of 6. We show that actually we cannot go to 6. Okay, then we have step 2. So assume the general fiber is 6. Again, we look at this map. So this is genetic surjective, and the 2 slopes are the same. It can only happen when this map is surjective. Okay, this should be surjective, and they have the same slope. And now what we can do is the following. So now this is has a rank 6 and degree 1. Okay, so if we consider the symmetrical power of this vector bundle, this is a semi-stable vector bundle, but it's a little bit difficult to study this vector bundle because it has splitting. It's no longer stable. What is useful is actually we can try to trivialize this vector bundle. Okay, in this sense, so it's actually a general fact. So if we consider the multiplication map on the identity curve, so this is the isogeny by times 6. So this is a very, very huge isogeny on the identity curve. Then the structure of this vector bundle becomes simple. So I write it as V. Pi star V, this is isomorphic to. Okay, so where L is a line bundle of degree 6. So so it means that the pullback of the vector bundle becomes trivial. So this is the direction of line bundle. And this isomorphic is actually canonical because so we need to think about this. There is actually a descent data here. So actually we have the Schrödinger representation action of C star E6 on this vector bundle. Anyways, this is there is encoded descent data here. Okay, so but now this map they have the same slope. So it means if we write K as the kernel of this map, so then the K pi star K. So it's actually under this isomorphism, it's actually it's W times L, where W is a fixed 6-dimensional subspace. Okay, so it's actually easy to understand because these 2 vector bundles have the same slope. The map here should be constant. So the kernel should also be constant. It cannot have variations. Okay, so now we can. Okay, so maybe I have spent 2 more minutes to explain. Is that possible? Okay, so if you consider the general fiber F, so we have the relative canonical map. Okay, so okay, in general this is just a map, but we can bilaterally modify a little bit S. We consider the relative canonical map. And the image of a general fiber is just the canonical map of F. Okay. And the K gives all the quadrics through the image. So there are several cases. Either, so maybe I should say, so there is so this is the old result. Petri, Babbage, and let me see. And Annikus. It says that so if we consider C, assume C is a non-hyperadiabatic curve, then consider the canonical curve. So the canonical map gives the embedding from C to P G minus 1. So most of the cases, C is skin theoretically cut out by the quadrics through C. Okay. In general, either C is cut out by quadrics through it. This is the most general case, or if not, then C is either trigonal or planquintic. These are the exceptional case. So this is actually the baby version of this the so-called Green conjecture. Green conjecture is the relation among CGGs of curves and the gonality of the curves. So this is the first step. Okay. So in general, the idea of C is given by the quadrics, but there are some exceptional cases where when C is trigonal or when C is planquintic. So in the general case, when C is cut out by quadric, we see that in our picture, all this K is constant. K is fixed. So if C is general, it means that all the fibers of S to E is the fixed curve. So all the curves are smooth. Then we have a contradiction. It means that the topological Euler characteristic, the topological Euler the C2 or S is 0, which is a contradiction. So if not, C could be trigonal or planquintic. But then we need some actual argument. So to rule out these two possibilities. Okay. So I don't have time. Maybe I should stop here.
Okay, thank you for the talk. So are there any questions or comments?
So there are examples for other genuses.
Okay. For other genus, so I should say when the okay. So first of all, I assume this C non-hyperadiabatic because there is the work of Ishida, Japanese mathematician, who studied the fibrillation S to E where the fiber is hyperadiabatic surface. So actually, Ishida shows that if F is hyperadiabatic, then the genus of F is smaller of 4, between 2 and 4. There are examples for 2, 3, and 4. So that's the 2, 3, 4 case. So I actually use this result because now I studied non-hyperadiabatic fibers. Okay, so this is the first genus case, and then when the Fujita non-trivial, we have several inducible components, and then in this case the genus is 2, 3, 2, 4. I don't remember. Anyway, there are 4 cases which are 2. There are 2 cases which are 3. maybe like looks like this. There are 4, 2, and 2, 3, and then 1, 4. The genius is like this. So, this is different. The genius 5 is different. But we can only classify all the genius 5 case. For other cases, 2, 3, 4, I guess there are many reducible components of the modular space. Now, maybe so many, but at least more than one. Yeah.
Any other questions?
You mean like in which sense? K-square is 5. So okay, so yes. So we have a version for theory B. But it's with a joint work with my student. So when the Fujita decomposition is non-trivial, we more or less we can classify, but it's no longer depends only on the type of the bi-elliptic surface. It depends on much more things. There are actually at least 11 family or when the Fujita decomposition is non-trivial. Yes. So basically in that case we first show that there is a canonical map to a bi-elliptic surface, which is of degree 3. And for degree 3 covers, we have a data of vector bundle. So yes. So we need to classify two vector bundles on bi-elliptic surface. In some cases, the surface exists. In some cases, the surface doesn't exist. So the number 11 appears. Yeah.
And then are you going to do K² equals 6 next? Or
No, it's very difficult because in 6 cases, I guess, so in 4, 5 cases, the unitary part is, if it's non-zero, it's just a line bundle. But my guess is to 6, the unitary part could be rank 2, I guess. I think so if you consider ample divisor in abelian threefold, if everything is smooth, then the ratio of volume and chi is 6. So if you can construct some appropriate group action, it's possible to construct a surface with Q equal to 1 and K² equal to 6, and the unitary part has rank 2. This is my guess, but I don't have this example. So when it goes higher, it's much more difficult. So even for 5, it's already very complicated. Yeah.
thank you. So any more questions? If not, then let's thank the speaker again.